All right, this is the first hour of Physics 1C for November the 29th. And tonight we're talking about AC circuits. And the word AC stands for, I think we've said this before in this class, alternating current. Okay. And this is going to be a type of current that we're going to use this symbol for, a little circle with a squiggly line on it. This is going to represent an AC voltage source. AC voltage source, or AC EMF. And the way that we're going to describe this one is by saying that there is a sine wave or a cosine wave that describes how the voltage is going to be. So in this case, we're going to write voltage as a function of time. So I'll try to write a lowercase v like this. Let me fix that just a little bit. So lowercase v to represent the instantaneous voltage provided by the source. And this is going to be equal to some V max. For capital V's, I'll put these two bars on top right here. V max, voltage max, times a cosine of omega times t, which means that the voltage as a function of time is no longer constant. The force on the electrons in this case is going to make it so that the electrons are never really going to go anywhere. The electrons are just going to go left and right and left and right and left and right, and the voltage will look like this. Oh, it's cosine function, right? So I should start it here. Right? And then it'll just repeat itself forever. And that means the voltage can sometimes be positive. So up here, this height from here to here is going to represent V max on this side. And then down here, the minimum of our graph is going to be negative V max. So what that means is, as I said, so what is a voltage source? We've referred to voltage sources up till now as EMF sources, right? And EMF stands for electromotive force. And this is the idea that the source itself is a thing that provides a force that pushes things around, right? And in direct current, the things are electrons. The electrons in a direct current circuit always go in one direction. In an AC circuit, the electrons just wiggle back and forth in the same place. And it turns out that you can still extract energy out of these electrons even if they never really move, even if they're just kind of wiggling in place. Because obviously that type of motion, that wiggling back and forth, it still can dissipate energy through a resistor, for example, or those wiggling of electrons can charge a capacitor and then discharge it and charge it and discharge it and charge it and discharge it. Or in the case of an inductor, these electrons can basically create a magnetic field that goes one way, and then when the electrons are flowing backwards, the magnetic field will go the other way, right? So AC alternating current, which you use an AC voltage source, is going to provide different types of physics for resistors, inductors, and capacitors that we've talked about up to this point. Now, when we look at these type of circuits, let's draw more to the circuit. Let's say that I put a full circuit in here. So I start off with my AC voltage source, so this is going to give me my voltage as a function of time. And let's say that we connect it up to a resistor. So here we have a resistor R. Well, that means that there's going to have to be current flowing in the circuit, and you could ask the question, well, what direction is the current flowing? And the answer is, well, it's always changing. So I'll just say that at a moment in time, let's say that we define the current to be I of t. And in this particular case, where I just have a resistor, we're going to find out that in this case, the current is just going to be this I max times cosine of omega t. Okay? If this is the voltage and I just connect up a resistor, my current is going to look like this. That means that the voltage and the currents in this case are in phase with one another. And I could plot them on the same diagram, where I could say from my pictures here, if this has a resistance R, and I have a voltage here, then I know that if I take V over R, that should give me the current as a function of time, right? So Ohm's law is still going to be true here, right? Ohm's law says V equal IR, so that means V over R equal to I. And if the voltage happens to be changing in time, the resistor doesn't really care, right? Some things we've talked about care about, how the voltage changes, such as inductors. But resistors just don't care. It's still going to be the case that Ohm's law still works. Oh, I didn't do that quite right, did I there? Sorry. Okay, so if we compare these three equations here, that tells us that if I find out what Vmax is, and I divide that by the resistance R, then that's going to give me Imax, right? So let's say that I tell you I have a resistance of like 50 ohms. If I then want to plot, so this is time on this axis, if I then want to plot the current as a function of time, the current as a function of time is going to look like this. Plotted on the same graph, where now that's going to be I of t, and the red line is V of t. So the height of this, if I can fit this in here, would be I max. And in this case, we would say that the current and voltage are in phase with each other. In phase. Out of phase would be if the current didn't reach its peak at the same time the voltage reaches its peak, maybe slightly before or slightly after. But you can see here that the zeros for voltage and for current both occur at the same time, so that's why we say they're in phase. And when the current is at negative maximum, the voltage is at negative maximum. When the current's at positive maximum, the voltage is at positive maximum, right? Okay, now in the class, if we think back to the very first lab that we did, you actually, in your first lab where you drew out the equipotential lines and the electric field lines in that big tub of water that we had, right? You may remember that I told you in that lab that it was alternating current. And nonetheless, when you went to measure your voltage, you didn't get a readout on your voltmeter that looks like this, right? If the voltage is actually alternating, then, and you plug in just a normal voltmeter, you should see the voltage basically go back and forth and back and forth. Or on a digital meter, it should be positive and then zero and then negative and then zero and then positive. But that's not what you saw. And that's because with AC circuits, we measure what's called RMS voltage and current. So RMS stands for root mean square. And to get an understanding of how this comes about, if, for example, we look at our current function here, right? So our current as a function of time is Imax cosine of omega t. If I want to find what the RMS current is, then I have to take the root of the square of the mean, okay? So what that means is I have to take my function here. No, you don't want to let me change colors? How about now? There we go. Okay, so if I want to take the root mean square, that means I have to take my function and square it. I then have to average the function, and then I have to square root it. That's what I need to do. I'll do the same thing on the left here. I have to square the function, I have to find the average of the function, and then I have to square root it. That's what we're going to do. And all of those things taken together are going to give me what's called my IRMS. Okay. So how do we do this? Well, if I have a function here, I max cos omega t and I square it, we know how to do that, right? I max squared cosine squared of omega t. So the question becomes, and you all tell me if you know how to do this. You may or may not have learned it in your math class. I don't know. I think it's usually covered in Calc 2. How do I find the average value of this function? What does that mean? What does that mean? It's a cosine function, right? It's a cosine squared function. What's cosine squared look like? I think it looks like this. So a normal cosine function would start up here and then would go down and it would become negative, but this one can't be negative, right? So normal cosine function would come down like this, right? But that can't happen because now we're going to square it. So I think cosine squared looks like these kind of like bumps like this, where instead of it dipping below the axis, I'm pretty sure this is what cosine squared of omega t looks like. Where this is t. And these would all be the same height too, by the way. They would all have the same height as I squared max. Okay, does that look right for a cosine squared function to you all? You go on your calculator and plot cosine squared x, does it look something like that? Okay. So how do I find the average value of such a function? Sometimes it's I squared max, sometimes it's 0, sometimes it's something in between. How on earth do I find the average value? How do we normally take averages? How do you normally take an average? Normally you just, if I have like 6 numbers, you would sum the numbers and divide by 6, right? Yeah, add up the numbers and divide by n. This is a function. So I suppose what we could do is we could take discrete values of the function, such as we could choose some interval, like from here to here, for example, and we could say, let's find 10 values of the function that are evenly spaced through here, sum up those values, and then divide by the number of values, 10. That would get us close to our answer. We want to be more specific than that. So there is a method in mathematics that you can use to do this, and it's about the same. Does anyone know what it is? How do you find the average value of a function instead of a discrete group of numbers? Does anyone know? An integral? Yeah, I mean, maybe we do an integral because, you know, a normal way we find an average is you sum things up and then divide by the number of values you summed up. But an integral is the same thing as a sum, really, right? So what if we do an integral? That's going to sum up the values. And then we need to divide by something. So what if we divide by the period? So the period of this function would be t. That's why I kind of broke this off right here. The period of a periodic function we call period t. And basically, if we integrate from 0 to t and then divide by t, can you see how that's kind of the same idea as doing an average? Sum up the function at all points where each individual point is a value of time. It's the same thing. That's exactly what I did. It's exactly what I did, Evan. I'll write it in another way so you can see how it's exactly the same. In the denominator here, you just have the difference of the limits, right? An integral from a to b and then 1 over b minus a, that is the definition of how you find the average value of a function over some interval. Okay? And because this is a periodic function that repeats itself, you know, we could look at the value over 2 periods or half a period or whatever we want. We'll always get the same answer. So the easiest thing to do is just use 1 period. And we need to do this with respect to time. And ultimately, we need to take a square root. Didn't you all have a problem like this in your... is it in this section? It's probably in this section of your online home or your Mastering Physics homework. I don't know if it's in this section or another section, but I think there's one where you have to find RMS current, and this is how you do it. Yeah, it's the one from the upcoming homework, right? So in that problem, you have to find, I think, RMS voltage and RMS current, and this is exactly how you do it. In fact, I think in a lab manual they tell you this is how you do it. All right, did I leave anything else off? I don't think so. So let's do this. Okay, how do we actually do this integral? It's really the integral of cosine squared omega t. I'm just going to jump to the end and say that you use a trig identity because we know that cosine squared of x is equal to 1/2. I never remember this. I think it's 1 minus cos of 2x. Is that right? I don't know. You all tell me. Does that look like the right trig identity there? I'm pretty sure where it comes from is this way. The cosine of 2x is equal to the cosine of x plus x. And the cosine of x plus x is cos x When it's plus here, it's minus here, sine x, oops, sine of x. But that's just cosine squared of x minus sine squared of x. So this is equal to cosine of 2x. But we also know there's another identity that tells us that sine squared of x is equal to, is it 1 minus cosine squared of x? So this becomes cosine of 2x is equal to cosine squared minus this is going to give you, wait, sine squared plus cosine squared is 1, right? Okay. So this is going to give you cosine squared, I'll just write it out. So we end up getting 2 cos squared x minus 1 is equal to cosine of 2x. So this is equal to cos squared of x is equal. You would add 1. Oh, is it addition? Maybe that was supposed to be a plus sign. So you would have 1 plus cos 2x, and then you divide by 2. Okay, so I think that's the identity. And you get it from doing the double angle formula. And the double angle formula gives you this, and you can rework it to get this. Okay, so I think that's right based on that, and I'm pretty sure this is right because we had to use the double angle formula this morning in my 1B class. Okay, so going back to what we were doing, the reason why I did this was because we can replace that in our equation here now. So now what we're going to have is the square root of 1 over t integral from 0 to t. I max, I'll leave this in here, although I could have pulled this out. I max squared. And now our cosine function has become 1/2 plus cos 2x over 2. Oops. I should really always use these curly 2's because they look better on the screen. Okay, there we go. Divided by 2 dt. Okay, and the next thing we can do, let's take this and we'll just cut it and then I'll move it off screen. We don't really need all the steps on the screen. Okay, doing all of that. Now, what is, so the first half of this integral is very easy to do. 1 over t I max squared. So 1/2 dt, right, is just going to give us t over 2. Okay, plus, this shouldn't be an x, right? My bad. Sorry about that. This should have been, it doesn't make any difference as it turns out, but this should have been cosine of 2 times, that's our x, omega t. There we go. Now what do we get when we do that one? Well, I can tell you we're going to get 0, because anytime you integrate a cosine function or a sine function over one period, you always get 0, right? I mean, you can see that from the graph of the cosine function. That's what a cosine function looks like, right, over one period. So if this point is t and this point is 0, if we go 0 to t, then you get positive area here, but it happens to be exactly equal to the negative area down here. So this is going to be 0. Doesn't matter if it's over 2 or multiplied by 50 or if this is 20 inside of here. It doesn't matter any of that stuff. When you integrate over one period, you're going to get 0. But in case you can't see that, what we can do is we can actually just plug the values in here. So the integral of cosine of 2 omega t, I believe, is the sine of 2 omega t divided by this piece. So divided by now 4 omega. There's still a 2 down here. I think if you take the derivative of this, you'll get cosine of omega t. We need to evaluate that one from 0 to t. Keeping in mind that t is equal to 2 pi divided by omega, then what we get is 1 over t I max squared multiplied by t over 2 plus, here we're going to get the sine of 2 omega period over 4 omega minus the sine of 0 for 4 omega. We know that the sine of 0 is 0, but this is also 0 because if 2 omega times t, well, the sine of 2 times omega times t, but t is 2 pi divided by omega, so the omegas cancel. So this is the sine of 4 times pi, so this is also 0. That means that our only term that we have left here for our IRMS, I'm going to change this to a capital sign now, our IRMS is going to be equal to, oh, and there was a square root that I left off, I'm sorry. This whole thing was square rooted. This whole thing is still square rooted. So our answer now is going to be the square root of Imax squared, which is just Imax. This t and this t will cancel with each other, so we just have over square root 2. Simple result. And this is what we measured with multimeters. As long as it's on the squiggly setting. That is to say, on your multimeter, I think for current, it looks like an A with a squiggle above it, and then for voltage, it looks like a V with a squiggle above it. These things are RMS values of the voltage and stuff. Okay, so to summarize what we have then, just to get away from all the math real quick, what we have is that VRMS is defined as the maximum voltage over root 2, and IRMS is defined as the maximum voltage also divided by root 2, okay? That's all you got to take away from that. Yeah, we did some math that may or may not have been particularly helpful. And honestly, what we could have done is I could have gone from this step here, and I could have just told you that the average value of the cosine function is a half. But I don't know, we proved it. So there we go. VRMS is just Vmax over root 2. IRMS is Imax over root 2. So if you look at United States, for example, in the United States, and this is different in other countries, it's different in Europe, it's different in Africa. In the United States, what we run off of is a VRMS that is equal to 120 volts, okay, which corresponds to a maximum voltage. If you take 120 and you multiply by the square root of 2, the square root of 2 is about 1.4. I believe you get 170 volts out of this. Let me just check. (120) times square root 2 is almost exactly 170. So in the United States, those are the values that we use. And in other countries, they use different things. I believe in the Europe, VRMS is 240, which means that Vmax would be what? Double this one. So 340 volts. And that's how we talk about current and voltage when we are discussing AC circuits, is by using these RMS values. And what we're going to find out is that if we use these values, then later on we're going to see that the rules about how you calculate things like power and how you do things like given voltage, find current, we're going to find that if you use these RMS values, that the equations that we get end up being very similar to the equations that we get for DC current. So that's a pretty handy thing about these RMS values. All right, so next thing we want to do, does anyone have any questions so far? All right. The next thing we want to do is to talk about phasors as a way to analyze AC circuits. Okay. The first type of circuit we're going to talk about is resistor only. Okay, and we kind of already did this, but we're going to introduce this thing called phasors to talk about them. So this would be a circuit like this. We have a voltage source that's an AC voltage source. We connect this up to a resistor R. We define the line current. I'll use a different color. The current flowing through here, draw it up here, we call I of t, and we say that it's equal to I max cosine of omega t. And we want to talk about how the current and the voltage are related to each other. Okay, we just saw that if that's the current, the voltage is also then given by basically this, which means in this type of circuit, V max is equal to I max times R. Interestingly enough, if we replace these with their RMS versions, you still get the same answer. VRMS is also going to be equal to IRMS times R in this circuit. And now let's draw our phasor diagram. Okay, so a phasor diagram is a diagram designed to analyze these type of circuits, and it's going to be a type of similar to a vector diagram, except the vectors can move. So let's take red, and we'll use that for voltage, and then let's use green for current. Okay, so two different arrows, one on top of the other. I'm going to say that my voltage as a function of time is going to be represented by the red line right here, and my current as a function of time, that's not exactly right, is it? No, that's not quite right. This is our voltage phasor, but what I'm going to say is that the length of this phasor, these are phasors, is going to be V max, and the length of my current phasor is going to be I max. Okay, and what you're supposed to imagine, I M A X. God, that looks awful. Just need to make more room. I M A X. There we go. Okay, so the phasor has length I max. The red phasor has length V max. Okay, that's how long the phasor is. So the bigger the voltage, you can make this longer if you want to. And now what we're going to say is that the entire system, these two phasors, which are going to be locked together, is going to rotate around at a speed of omega. So this entire thing is rotating, okay? And it rotates around such that its angular frequency is omega, right? So we take these arrows and we imagine that they're just rotating around in space like this, right? That's what we call a phasor. And then what we can do is we can say, if I take a projection of my Vmax down to the x-axis like this, right here, and I also take a projection of Imax down to the x-axis like this right here, then because the current is cosine omega t times Imax, and the voltage is cosine omega t times, this is Vmax, then the length of this line down here at the bottom, all right, kind of lower down here, is going to be the instantaneous voltage. Oops. So this is equal to Vmax times the cosine of omega t. And that is going to be the length of this line right here. And as the phasor rotates around, the length of this side here is going to get, well, as it rotates in this direction, it'll get smaller until it becomes 0. And then eventually the phasor is going to point over here, right? And if you look over here, the projection on the x-axis will be this, and it's still going to be equal to that. And then eventually the phasor is going to rotate, it's going to keep rotating. It's going to rotate like up like this, and then this way, and then this way, and eventually it's going to be down here. Take this projection here, that's going to be the voltage. Eventually it's going to be down in this quadrant. So I drew a bunch of lines on there. That wasn't too confusing. The idea is that the projection onto the x-axis gives the instantaneous voltage. Right? And in this case, both the voltage phasor and the current phasor are going to be in phase with one another as they rotate around. Okay? Okay. Did any of that make any sense? We also have the instantaneous current down here too, by the way. This is I of t. From there to there. Because it's the projection, right? If this angle is omega t, and this is I max, then the length of this side would be I max cosine omega t. Can you all see that? And can you see how the rotation of this, as it goes around and around and around and around, at any moment in time, if you stop time, this phasor turns into basically this, right? Okay. So it's pretty clearly not, I'm not saying anything groundbreaking or new, because obviously if you take a point in the xy plane and you draw a circle in the xy plane, like the unit circle that you learned about, right? Then a vector drawn from the center out to the circle will always have components that are given by, you know, something cosine theta and something sine theta, right? So this is just the nature of how vectors work. But what makes it a phasor, right, is the fact that it rotates in this space. Now, you may notice also that I didn't label these axes here, right? There's no label for the axes. And that's intentional. The axes don't have any meaning. This is kind of like it's like a phase space where we're going to use it to allow the phasors to rotate around, but the axes themselves don't have any meaning in this. We're not graphing things, right? We're just looking at how a phasor rotates in this space, okay? All right, so in phase, current and voltage. Really simple for the resistor only. The interesting thing happens when we switch and we talk about something like an inductor. So the second step is inductor only. And now this is where the AC circuits start to get pretty interesting. How much time do I have? We started at 1:15, right? So plenty of time. So for the inductor only circuit, what we have is voltage source, again, V of t, a current, and an inductor. Inductor L. Okay. All right. So again, we'll have current flowing here. I of t. And now what we're going to do is we're going to say, let's assume that the line current is given by the same thing that we had before. So let's say that that's our current as a function of time. Now the question is, what does the voltage as a function of time look like when we talk about the voltage of just the inductor? Okay, that is to say, suppose that I were to put in my system here a voltmeter that measures RMS voltage, right? And I call this the voltage across the inductor, so that's VL, right? The question is, what is VL going to be equal to? VL of t, I should say. And for this, we're going to say that it has to be equal to, we learned this relationship that the EMF for the inductor is, the back EMF, right, is, what is it, negative L di dt, right? And we have current. So we're going to say in this case that this is the voltage across the inductor that we actually read here is going to be positive L times di dt. Because after all, what the inductor does is when you have changes in current, the inductor is going to have a resistance to that change in current, and we have a current that's changing here. So the voltage across our inductor is going to be equal to whatever the inductance is times the derivative of this. So it's going to be this right here. And now we can say that is positive. Wait. That's wrong. That's wrong. This is wrong. What's wrong with this? The derivative of cosine is negative sine, right? There we go. Okay. Now what we're going to do is we are going to use a trig identity that says that negative sine of x, this is where I have to think about what this looks like, is equal to the cosine of, it's shifted to the right? Negative sine. I think this is going to be x minus pi over 2. I could be wrong, though. Does that look right to you all? Or is it plus? So normal sine functions like this. The negative sine function looks like the opposite. So that's negative sine. And a cosine function. So it's shifted by that. This can't be right. Is it right? Because this would shift, the cosine function would shift. I can't ever remember. I think it's actually plus. That's what the book has, is it's plus. Cosine of a plus 90 is equal to negative sine a. Okay, well I can't remember it off the top of my head, so we're gonna trust them that this is actually the right answer. We could prove that identity too. If we want to, how can we prove this one? Do we want to prove this one? Do you all care? It's not hard to do though. We might as well do it. This is cos x, cos pi over 2. This is a plus sign, so it's minus sine x times sine pi over 2. Okay, this one's pretty easy to prove, isn't it? Because cos pi over 2 is 0, and sine pi over 2 is 1. So you get negative sine x. Okay. That's correct. So this is true. And given that this is true, my equation down here, my instantaneous voltage equation, the voltage across the inductor, should be equal to, I'm going to write it as omega, let's see, IR. So I want to write it as I max times omega times L multiplied by, we're going to change negative sine omega t to cosine of omega t plus pi over 2. You could write it as plus 92 if you want to. But that's our expression. And we can draw a phasor for this situation too. So now if we consider what we have going on here, this is our current. And this is our voltage. Right? So if we plot these onto a Phasor diagram, this is what it will look like. So first thing I'm going to do, I'm going to start off with the current phasor and leave it in exactly the same orientation we had before. So we're gonna make it look like this here. So current phasor, using green again, goes this way. So that's going to be my current. This one has length I max. And of course it rotates at a rate of omega, so the angle made here is going to be omega times t. And now, what did I use? I used red for voltage. So now using that again, for my voltage phasor now, my voltage phasor needs to be pi over 2 ahead. So I'm trying to make this a right angle right here. It's really hard to do. Looks like that's probably right. So this is going to be Vmax. Oh boy, I hate writing these little... Here, just erase it. The length of this one will be Vmax. And now, since this is a right angle, what'll happen is that arrangement, where you have this like L here with Vmax going this way and Imax going this way, the whole arrangement's just going to rotate around. So this whole thing is going to be rotating in this direction, and this one's going to be rotating up this way. They go around in a circle, and just like before, if I look at the projection down here, I'll get I of t. That's what that projection is going to be, right? And on the other side, if we come down here, then this little segment right here is going to give us the voltage as a function of time. Because the voltage as a function of time should be the cosine of the angle omega t plus, here's the pi over 2 right here, right? So omega t plus pi over 2, then this is going to give you the voltage when you take the cosine of that. And what we can say is that the voltage, this is VL, what we can now say is that the voltage across the inductor leads the current by pi over 2, or by 90 degrees. The voltage across the inductor leads the current, the line current, by pi over 2. As we see this pi over 2 show up here. Okay. Does that make sense? The voltage and the current are out of phase. That's another way of saying it. If we compare that to, let's go back to the resistor. For the resistor, this was the current. It has a cosine omega t. This was the voltage. It also has a cosine omega t. The phasors lie on top of each other, so we say that they are in phase. They always lie directly on top of each other. When we have the inductor, what happens is that the voltage across the inductor now leads the current. And this is, of course, because what does an inductor do? An inductor resists changes in voltage. So when the voltage is trying to change, the inductor doesn't immediately allow that to happen. There's like a time lag between the applied voltage versus the voltage that's actually set up in the inductor, and that's what this pi over 2 is. Okay, does that make sense? Anyone have any questions? Okay. The next thing that we're going to do is we're going to look at that piece right there. So notice that we have this in the voltage function. We have this overall factor here, which is basically the amplitude, which is Imax times omega L. So we know that has to be the maximum voltage because cosine omega t plus pi over 2, the biggest this can be is 1. So this must represent the maximum voltage. So what we can say is that Vmax is equal to Imax times omega times L. And now what we want to do is we want to make this equation look like our equation for the resistor. For the resistor, what we have is Vmax equals Imax times R, right? So what we're going to do is we're going to define omega times L to be equal to X sub L, okay? We call this, you may or may not have heard it, we call this reactance. This one's called inductive reactance. Omega times L equal to XL. This is called inductive reactance. All right. And given that type of thing, we can rewrite our voltage equation as just I max multiplied by XL. And this allows us to have an equation that is really similar to V equal to IR, right? But it's an inductor. So it turns out to be the case that omega times L, the frequency of the circuit, multiplied by L, is this thing that we call inductive reactance. And I like to think of this as a way to turn an inductor into a resistor, in a way. Reactance is kind of like generalized resistance. And what this is telling us is that, I like rewriting it in the following way because I think it's easier to understand. If I write this as I max is equal to V max divided by this thing called XL, this tells us that for a given voltage, let's say that I tell you the voltage here is like in America is like 170 volts, for example. I'm running off the screen, so I'll scroll down a little bit. Let's say that I tell you V max is 170 volts, right? Well, I can find the current if I just know this quantity in the denominator, right? So let's say that this quantity in the denominator has units of ohms, by the way. I should have said that. This has units of ohms. So if this is 170 volts and this is 100 ohms, then you're going to get a current of, what, 1.7 amps, right? And if you were to reduce X sub L, if it was like 50 ohms, what would happen to the current here? The output current. If I change this to 50, the current's going to get bigger, right? So the smaller that the inductive reactance is, the bigger the output current's going to be. Isn't that exactly like the way that this equation works, right? This equation, the way that it works here, let's use a different color. This equation here, the way that it works is to say that the current that you get out is directly proportional to the voltage given divided by the resistance, right? So this is kind of this thing that we call reactance, X sub L. It's kind of like this generalized version of resistance because it tells us the effect of putting this inductor into the circuit is going to be that the bigger the value of the inductor is, the smaller the output current you're going to get. And the other piece of it is this omega right here. So let's figure out why that's in there. Why does XL depend on omega? Well, the bigger the value of omega, the bigger the value of XL, right? So if the frequency is doubled, the inductive reactance is doubled, right? Why is that the case? What it's telling us is that when, oh my god, I can't write today. When omega is big, XL is big. Why is that the case? Well, what does an inductor do? Inductor doesn't resist current. It resists changes in current, right? So when the frequency is big, what does that mean? Big frequency means that you've got a current that's oscillating back and forth and back and forth and back and forth, right? That's a big omega. And when you have big, sharp, spiky changes, then the derivative of this thing is going to be large, which means that the inductor is going to do more, right? Because if you have really fast changes of current, the inductor is going to produce more resistance in your system, more back EMF, right? Does that make sense? Does that seem logical to you all? When frequency is large, more back EMF, which means your output current's going to be lower. That's how it's all tied together. Did you all follow that? Inductors resist changes in current. When omega is big, that means there's a lot of change in current. As a result, XL becomes large, which means that the inductor's effect on the circuit is that it's going to lower the output current. Right? It all comes back to this right here. So this is really interesting, right? Because I think that the idea of what an inductor is in a DC circuit is quite complicated. But in an AC circuit, when the current is always changing, the effect of the inductor is it kind of just acts like a resistor. Not exactly. It's not exactly the same. It's not like saying, but I mean, the units of this thing have the same units as the resistor. The form of this equation, I max is V over XL, is exactly the same as the form of this equation. It's an easier way to describe what that inductor's doing without having to think about Ohm's law, without having to think about Faraday's law, without having to think about all the things that go into inductors, back EMF, and all that stuff. All right, so I think that makes sense as a place to stop. And then when we come back, let's talk about the other part of this. The other half of this is that when omega is small, XL is small. And the reason for this is because when the angular frequency is very gentle, right? So this would be like something like this. When the angular frequency is very gentle, then that means that the rate of change of your curve is going to be small. And when the rate of change is small, that means the inductor just isn't doing as much. The inductor has plenty of time to get its magnetic field set up, and then plenty of time to release the magnetic field without big spiky changes. All right, so we'll take a break there. When we come back, we'll talk about capacitors, and then after we talk about capacitors, we'll put all three together and see how they behave. The key thing to take away from this that we're going to be using later is that the voltage across the inductor leads the current by pi over 2, and these phasors are going to be useful to us in kind of putting all three together, right? So take a break, 10-minute break.